Good day, Math 30-1s. Today we talk about combining transformations, or if you like to farm, combining transformations. Now the point of today is to sketch and create equations of transformed functions by applying all three things: translations, reflections, and stretches, vertically and horizontally, resulting in up to 6 effects. Now you are expected to be able to do reflections, stretches, and shifts in one question. First thing to maybe examine is, does order actually matter? Can you stretch before a reflection? Can you shift before a stretch? Is there really any order? So let's ask, does order matter? And really simplify the question. What if we follow one point, the point 3, 4? What if we take this point, we'll call it point A, and say, what happens if, in a first scenario, we stretch vertically by a factor of 2, reflect horizontally, and then shift left 2 units. So stretch, reflect, shift. We're going to apply the same effects to the same exact point, but in a different order. We're going to go backwards and shift, reflect, stretch. Will we end up at the same place with the same effects in a different order? Well, our first effect is to stretch vertically by a factor of 2. So this point would stretch up from a 4 to an 8, and we'll call it A prime. After that, we have a reflect horizontally, which flips this horizontally from a 3 to a -3. We'll call this A double prime. And then shift left 2 units, 1, 2. And we'll call this our A triple prime, our final result at -5, 8. Do we end up at the same place? Maybe order doesn't matter. What if we shift left 2 units, 1, 2, call it A prime, reflect horizontally, so from a 1 to a -1, A double prime, and stretch vertically by a factor of 2. So the 4 stretches up to an 8. Are we in the same location? No. Does order matter? Yes. Now, what we're essentially doing is following the order of BEDMAS in a way. We are going to be doing our multiplying and dividing before we do our addition and subtraction. So one of these answers is technically supposed to be correct, and according to BEDMAS, we are going to be doing these reflections and stretches before any shifting. So a general equation for transformations looks something like this. We are going to have some function created with a b value, stretching, flipping, an a value, stretching, flipping, this time vertically. There's a horizontal shift, a vertical shift, and again this k could be on the other side in a different position at times. And things we need to be aware of. What do you need to remember about the position of b? In this format, we actually need to have the b value factored out to correctly see what the proper shift is. So if I gave you a function like this and said, tell me the horizontal stretch, I would see a b value of 2 and say it's a horizontal stretch by a factor of 1/2. If I said, what's the horizontal shift? If you said it's a -6 or 6 to the left, I would say, all right, there's something to fix. We actually will need to see that factored out so that we can properly say it's 3 to the left. So there does need to be a factored form to properly see the horizontal shift. What do we need to remember about the position of b? Well, maybe just say it needs to be factored. What do we need to see about the k? It could be on the left or the right. So there could be this idea of left-right positioning. And we saw this in our first lesson in 1.1. There is a left or right positioning. If you saw the k on the right side, if it says +5, it's up 5. If you see on the left side, y subtract 5, that still means up 5. And that is a little bit tricky. So the last, again, comment about order, the stretches, A and B, and the reflections, with A and B must occur first, as long as the translations occur after. So let's try these in a few examples. And I do have a function shown. This is actually the square root of x graph, and I call this function f of x. Question is, what happens to create our new function? And whether I call this g of x or just say it's the new y values, we're going to be dealing with a negative in front of the f of x, which implies a vertical flip or reflection, and there's also a plus 3, up 3. So what has to happen first? Flip or the shift? The flip. So what we'll do below is we'll maybe redraw the original function 0, 0, 1, 1, identified a few points above, 4, 2, and 9, 3. You might actually notice that's sort of the opposite of a parabola. We'll come back to that in another unit. So there's your radical function, and this is our original function f of x. I'll call it as such. So if we do a vertical flip, we will start to see 0, 0 doesn't move, 1, 1 flips the y value under, y value of 2 to a negative 2, y value of 3 to a negative 3. And here is the vertical flip. After this, if we were to shift this up 3, we would take all these points and actually count 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. And do your best to draw a nice smooth curve connecting the dots. And this is your final graph. If we wanted to give this a name like g of x, we can now say this is the graph g of x, the final answer. That is applying two transformations, a flip and a shift. Let's continue with maybe a few more trickier examples. And when we look at a harder example, we have a new function, which again we can give it a new name, but we'll leave it as y for now. We might ask, first, that 2x plus 6, bit deceptive. Let's first write it in the form with maybe the y minus 1, moving that k over so it's a little bit more comfortable, and let's factor out the b value. So if we do that, we have nothing in front, so a value is 1. A value is 1. We factor out a 2, which leaves us with an x plus 3. And then we add the 1 over to the other side so that we can see all the different values. The a value, can't see anything, so it's a 1, an implied 1. The b value is a 2. The h value, it's an x subtracting a negative 3. X subtracting a negative 3, which appears like an x plus 3. And there's a k value that is a positive 1. What are the changes to apply? I notice for the shifts, and that we'll deal with those after, but for the stretches and flips, there's no a value other than 1 to deal with, so maybe we'll only deal with the b value of 2. That is a horizontal stretch by a factor of b value is 2 by a 1/2. We're also going to shift 3 left and up 1. Shift up 1. And so using the previous function, what if we were to apply all these effects? So it might be, again, a little bit tricky, but we'll give it our best shot. 0, 0, 1, 1, 4, 2, 9, 3. Sketching a smooth curve. What does it take to do a horizontal stretch by 1/2? All the x values are multiplied by 1/2. So the 1 becomes a 1/2. The 4, the x value of 4 becomes a 2. The x value of 9 becomes a 4.5. And maybe a little bit tricky, the next one would be 16, 4, and that 16 would come in a bit tighter and become an 8. That's a bit of an extension. That's as best we could probably do for the horizontal stretch by 1/2. Can we shift this left 3 and up 1? Maybe we'll try to do this all at the same time. Left 3, 1, 2, 3, up 1. Left 3, 1, 2, 3, up 1. Left 3, 1, 2, 3, up 1. And I think that's as best as we could fit. 1, 2, 3, up 1. Okay, that's the best we could fit. This is your new function. Now, it can again get much more complicated, but this is now applying 3 effects. As you take a deep breath, what would happen if we examine something maybe as complicated as this? Now, if we were to deal with something specific like x squared, something comfortable, when we look at something more complex, we could ask, all right, the equation notation of the transformed function. Now, if we were to say, what is the actual equation, we could say there's a vertical stretch by a factor of -2. So if we're dealing with the exact equation, we're talking about a parabola. There's a b value of 1/3, an x minus a 4, tucked in there, plus a 1 after. So in the input, we're seeing a 1/3 x minus 4 in the input, plus a 1. This is not something we ever really dealt with last year. So this is a little bit maybe too unfamiliar, uncomfortable. But there's a vertical flip, a vertical stretch, a horizontal stretch, shift right, and shift up. So what we're going to do is use mapping notation to say, you know what, I want to draw one graph, the final graph. We can actually say, I know how every point's going to move if we use mapping notation, what's actually happening. I know that all the x values are being multiplied by 3 and then adding 4. All the x values are multiplying by 3 and then adding 4. I know that all the y values are being multiplied by a 2, a -2, and then up 1. This is happening to every single point. So why not look at a couple points on a quadratic, which is input squared, and I chose these 5 points at random. They're centered around the origin, and we'll just see what happens to them. So if I take all the x values and say this is going to happen, a 3 times the input plus 4. So 3 times -2 is a -6 plus 4. 3 times a -1, -3 plus 4. 3 times a 0 plus 4. 3 times a 1 plus 4. 3 times a 2 plus 4. These are all the new x values as those points were transformed. The y values are being multiplied by -2, and then we're adding 1. So a 4 times a -2 is a -8 plus 1. 1 times a -2 is a -2 plus 1. 0 times -2 plus 1. -2 times 1 plus 1. And a -2 times 4 is a -8 plus 1. And if I sketch these 5 points, I should see the final graph in one quick step. So, a -2, -7. 1, -1. 4, 1. 7, -1. 10, -7. And I actually do see a parabola. A bit of a smooth curve connecting all those dots can give me a little bit of confidence to say, I did all that in one step. And that's the power of mapping notation. Maybe as a last example, we'll look at the bottom example, which talks about moving a point. So the point 2, 3, if we said that that's on some function and it's shifted based on some crazy transformation on f to create g, where's the new point on g of x? So we've talked a lot about moving functions, but I really want to be clear that when you're moving a function, you're still moving points. And the mapping notation is the effect of moving not just a point, but a function. So if I can look at all the effects that are happening to this entire function, I see that there is a vertical stretch by 3, there is going to be a horizontal stretch by a factor of a half, left 1, down 1. So all the x values are being multiplied by a half, and then left 1. The y values are being stretched by 3 and down 1. So this does take a bit of time to get to a comfort level to do this quickly. But we can say that not only is the entire function moving this way, but even one point. So sometimes we can feel like a question is more complicated than it needs to be. And this one point has an x value being multiplied by a half, down 1. So the 2 is being multiplied by a half, down 1. The y value is being multiplied by 3, and down 1. And that's where the new point ends up. So a single point can be moved through mapping notation instead of trying to sketch things, because in this case, we don't actually have a function to sketch. Good luck in combining mapping notation.